Hello everyone, hope all of you are doing fine and practicing mathematics regularly. I'm back with our exercises examples, that is 6.2 application of derivatives you have been doing so far. And today we'll start with our example 8, very first example of this exercise, in which we have to show increasing and decreasing functions. Alright, so let's start. This is the statement of our eighth example, that is, we have to show that the function given where x is belonging to R is strictly increasing on R. In our previous video, we have discussed the parameters with which we can prove a function to be increasing or decreasing. So if you have not watched that video, I would really recommend you to go and watch that video and then come back for the examples of this exercise. So firstly, according to the previous video's rules, we will find f dash x. It will be 3x square minus 6x plus 4. That is, we have differentiated the function. So we get f dash x is equals to 3x square minus 6x plus 4. Okay. And after that, now we have to find that if the function from any value of real numbers of x will be increasing or decreasing. That is, we have to check whether f dash x is greater than 0 or f dash x is less than 0 for all r, or you can say for every interval of r. All right. Now, put any of the real numbers, any negative or positive as well. In book, they haven't given any kind of example. So to help you guys, I will be taking some examples for you to make this concept understand more clearly. For example, suppose x is equals to 2. So 2 square minus 6 multiplied 2 plus of 4, what we will get? 2 2s are 4 minus 12 plus 4, that is 12 minus 12 plus 4, that is 4, which is greater than 0. Alright, now we have taken a positive value, that is the smallest positive value. We can take 1 as well. So then also our answer will be positive. And now let's take a negative value. For example, say minus of 1. Now 3 minus 1 square minus 6 minus 1 plus of 4 is equals 3 plus 6 plus 4, that is any which way is positive. So it doesn't matter whether you take positive value or negative value, your f dash x is always coming out to be greater than 0 on every interval of r. That is why you will write the function is strictly increasing on R. This is how we have to show whether a function is increasing or decreasing. It's looking very simple, but when we'll move further, we'll get trigonometric functions. That's a bit tricky part, but don't worry, I'm here to make that easy for you. And so let's move to the next example. This is our next example, example 9th. In this, the function is given as cos x, and we have to show that this is strictly increasing on this interval 0 comma pi and strictly decreasing in this interval pi comma 2 pi. There is also a third part of the statement of this example 9th, and we will do that after doing these two parts. Alright, so firstly we'll do the a part, strictly increasing. Now for everything to be proven, we have to find f dash x. So fx is cos, so f dash x will be minus of sin x. Alright, you know that cos x differentiation is minus of sin x. Now we will prove parts one by one. Firstly, we'll take this interval 0 comma pi. Now it's an open interval, so the values on the edge will not be counted. So let's take pi by 2. Now at pi by 2, minus sin x is equals to minus of sin pi by 2, that is of minus 1. It means f dash x is less than 0 in 0 comma pi, which means fx, not f dash x, fx is strictly decreasing in 0 comma pi. We have proved our first part. Let's move to the second. Now here the interval is pi comma 2 pi. So take any value pi comma 2 pi, take 3 pi by 2, or you cannot consider these values. So what is f dash x? that is minus of sine x. So what you will get, minus of sine 3 pi by 2. Now again, sine 3 pi by 2 is some positive. Sine 3 pi by 2 will be a negative value according to sine wave. So if sine 3 pi by 2 is a negative, then whole of this value will be automatically greater than 0. It will become positive because sine 3 pi by 2 is negative according to sine wave. You can check that. So it means fx is strictly increasing in pi comma 2 pi. Now let's have a look at the C part. What is C part saying? In C part, we have to prove that it is neither increasing nor decreasing in this interval, that is 0 comma 2 pi. Now we have taken two intervals, 0 pi and pi 2 pi, but here we have to take interval 0 comma 2 pi and we have to prove that it's neither increasing nor decreasing. For this, you have to take both of these intervals as closed intervals, 0 comma pi and pi comma 2 pi. And you have to observe the value of functions on both of the endpoints, because now it's a closed interval, we can consider endpoints. So what was the function? The function, not the differentiation, the function was cos x. Now cos x is when x is 0, so you will get 1. When x is pi, you will get -1. Okay, so it's neither increasing nor decreasing. It has varying values, 1 and -1. Same in this case, that at cos pi you will get -1 and at cos 2 pi you will get 1. So it again means it's neither strictly, what was this interval for? This was for strictly increasing. So it's neither strictly increasing in this interval and nor strictly decreasing in this interval. So that's why in your book they have written that from A and B, it's clear that f neither increases nor decreases in 0 comma 2 pi. This is how you can understand this concept, but in the book they have only written this thing, that this is clear from A and B. So this is how they have written this. So now you are able to do sums like in which you have to prove that function is neither increasing nor decreasing in the combined interval and in the individual intervals as well. So let's move to our next example.